So they're so disingenuous about everything. Okay, the percentage, the wave function is this. This is the wave function. It's a percentage of, it takes a position on this graph. Every position assigns a probability percentage that the electron will come through here, or the photon or whatever, and will hit there. That's all the wave function is, just like in Nevada, okay? And the wave functions in Nevada are not smeared all over. The customers and gamblers aren't smeared all over, and they don't exist until they start gambling or, spending money at the store or the casino, okay? They exist just like the electron, okay? So far we've proved, I hope, that the electron, it's a particle, right? It's a particle. The path is a wave because it oscillates, okay? This isn't my thing, like I came up with this idea. They say that the electron is vibrating, not me. I'm just repeating what they say, okay? And they also say, as we saw, that wave equations, the wave function, it works on solids that vibrate as well as actual waves, like in a water thing, okay? So I don't understand. What's the deal, man? If the equations work out whether it's a solid vibrating or a, this magic, why do people pick the magic? You have two choices. You can choose that the electron is vibrating. That's why you can't see it, and that's why it obeys does this stuff here instead of having, two things up here, with your double slit. Everything is explained easily by the common knowledge that every physicist agrees the electron is vibrating. So why do we make up this magic? Okay, right? Now the photon, light. I haven't decided yet whether it's a particle or a wave. You know what I mean? It's obviously different though than the electron. Okay, this idea, like with the photoelectric effect, that proves that it's a particle. That doesn't prove shit. It could have came in at a wave, hit the electron and boosted it off, and then the rest of the wave just went on its way, did its whatever, just continued on. Like, let's say this was the electron, the photon's coming down, it's going to kick off an electron. You can see it could just break off right where that orange line is. You could just break that off, right? Absorb that much energy, and then the wave still goes on. Just like if this guy was standing in the water, right? Here comes a wave against this guy, right? He could just take out some of the wave, and the rest of the wave just goes around him. You know what I mean? We don't sit around saying, those waves must be particles then because he just absorbed some of it. It's like, no, just because he absorbed some of the wave doesn't mean that they're not waves anymore and they're particles. They always jump to conclusions that they shouldn't jump to, okay? That doesn't, the photoelectric effect does not prove one way or the other, okay? It just proves that if you throw ping balls at something that's heavily weighted down on the bottom, it might not tip over. You can throw a billion ping pong balls at them, but it won't fall over unless you throw a baseball because you need a certain amount of energy. But if you have a hose of water, right, you can have it streaming out and it still won't hit that same bottle that's heavily weighted down. It's not going to hit it off. But if the stream is really high, then yeah, it will hit it off, okay? Just like a wave, if the photon is a wave, it can wave on down to the electron, boost him off, and the rest of the wave just continue on. Some of the wave broke off, right? Why do they always jump to these stupid conclusions? Okay. Now, before we go on, I want to reiterate that this guy right here, the only way that you can get one pattern like here or one bunch over here or both bunches like that. Okay, first of all, if you're a guy here shooting a bullet, right, and you're good with your aim, you're not going to have two clumps. You're going to have one clump. Whatever slit he chose to shoot on, that is the clump view or whatever, right? And it'll go right there. Or if he chooses this slit, it'll go over here. Okay? But even that, okay, if you compare it to the single slit experiment, right? Okay, yeah, sure, if these are big enough, but we make the slits so that they're so tiny that they're barely bigger than the thing that you're throwing it through, right? So if we did that, and this guy, I don't care how good of an aim he is, if the slits are as, like the slit is this wide and the bullet is this wide, they're going to hit off of the sides a bunch of times, and you're going to have a scattering effect, okay, which we've proved from looking at the wave equations. Scattering happens with solids. You are going to hit the sides a bunch of times if the slits are small, and you're not going to, I don't care how good you are, you're not going to have a clump here or a clump here. It's going to be an interference pattern like this. It's going to go all the way up and down, you know what I mean? More in the center, right? The only way you can get a clump like this is to have a big enough slit, which means you have no slit, right? If your slit is so big that your particles aren't hitting the sides, then you might as well say that you have no slit. You just have open, it's just open, right? That's the only way that you can get this, okay? A single, where they're talking, this stuff where they say you're going to have two piles here or just one pile, that's non-existent, that's a lie, okay? There's no way in hell, and what's funny is, these people like Science Asylum and, PBS Space, they know that if you have the slit small, you're going to have, they know that, come on man, if your bullet is this big and then the slit is this big, basically the same size, it's going to hit the sides a bunch. You're not going to have two clumps like this, okay? And when you do the, two slit experiment, this green part is the actual laser, right? And these are your two slits. You can see the laser encompasses both slits and all right. You're throwing trillions of photons at these slits, right? And they're all in this circle, okay? They're not just coming out of a bullet, because if you had this gun, it would just be one little tiny photon or whatever, you know what I mean? No. You would have to have a gun like this, where it's actually circular, you know what I mean, where bullets are coming out all over the place so that you can have a spread as big as this laser circumference, right? And now, if you do that, you're not going to get this. Why would anyone with a PhD, these people like Science Asylum, he has 5 PhDs, and yet he says, oh, you know what? If you do this experiment, you'll have 2 clumps. No, you won't have 2 clumps. These bullets are going to be flying, or whatever you're shooting, it's going to be flying all around. A lot of them are going to hit the sides, and you're going to have an interference, pattern, obviously. Okay? So, the thing I want to get to is okay, they are lying left and right. Why are you listening to them? Right? They compare the electron to a baseball that is not vibrating. That is disingenuous. That is a lie. Okay, that's an obvious, you can say it's a mistake all you want, but these people know the electron vibrates, so why would they compare the electron to a ball that is not vibrating? Okay, that's number one. Number two, even if the ball isn't vibrating, like we said, you'd have to have a spread like this, right? So you have hundreds of baseballs or bullets or whatever, and they would come over here, they would hit the sides, no matter what you do, whether you're him, no matter what you do. Even if you just throw one bullet at a time. If the slits are tiny, you're going to have an interference pattern because the bullets will be interfered with by the sides of the slits. That's common sense. To think that you would throw a barrage, you'd have a gun like this throwing a barrage of bullets at these 2 slits, and they're just, none of them are going to interfere and deflect off of the sides, is insane. That is, I don't understand how I'll have 7 billion people on this planet that think that you can do that, and none of the bullets, none of them will be deflected by the sides. It's insane, and you will have 2 patches here instead of an interference pattern. That is a total lie. Okay, that's insane to even think that. Vibrating solids use the same wave equations, scattering, interference, all that kind of crap. Okay? The wave function is a graph. All right? It's a graph. The electron is a particle, not a graph. Okay? A graph cannot be spread all over the the area, or volume of area, or whatever that the electron is at. No. because the electron's a particle, okay? So it doesn't get smeared out. It oscillates, so yes, it's never in that same spot. It's because it's, even if standing still, it's oscillating, so it's moving up and down, right? It's moving from position to position, you know what I mean, and back and forth like a wave, okay? I want you to understand, before we go on, let's say this is a camera, right? And you take a picture, you have a big opening, right, for your camera. And this is your plate, your photo plate. When you have a big opening like that, you get a good picture of the guy right in the middle, but all this stuff on the fringe, all at the ends, it's all blurry. You know what I mean? You can't make it out a lot if you have too big of a thing here, right? Why is that? Because the photons coming from this side and that side, they're going through this giant opening, and they're not hitting the photo thing. They're not hitting this. See how it comes down, and boom, it's not, a lot of it's not, some of it is, but not a lot of it. But look down here where you make the thing small now, right? You make the opening small, the slit small. You got your photo thingy here. Now you get clear background on these fringe, on these ends here, right? You can see they're trees now, okay? Because the photons come in, the hole is so small, it bangs off the side and goes back. Same over here, boom, boom. They just get, they get deflected now. These over here, the photons coming from the sides weren't getting deflected. They were just getting lost. Here they're getting deflected and collected onto the plate. So it focuses out the, you know, the whole picture, so you can get the trees instead of this. So the smaller the hole is, the more you can see of the background. The bigger the hole is, you lose the background. It's the same way over here, okay? When you have a big giant hole like this, right? I want you to look over it. Look at that. You have a big giant hole. Now the laser goes through the hole, and you just basically get a dot on the wall because it's not interfering with the sides, right? It's not touching any. You can see the laser's not touching the sides, right? But let's say we make the hole smaller. We make the slit smaller. This is, even though it looks the same size, this is a smaller slit than that, okay? So now that circle is bigger than the slit, right? So now some of these things that at the very edge here that weren't hitting the sides, and over here these weren't hitting the sides, now they are hitting the sides, right? And you're looking at this slit is that thick. That's what this thickness is. You can see the floor and the wall, right? Because you're up a little bit higher and to the right over here, and you're looking down on it, so you can see that thickness or whatever. At first, you know, as you make it smaller and smaller, this slit, and at one point, you're finally going to get some photons hitting it doesn't hit the outer part of it. It goes all the way through the slit and barely touches the side. And what happens? It gets deflected, but only a little bit, right? So instead of coming straight in, right? See, he should be coming straight in, right? And barely hitting that end at the end there, and he gets deflected, right? Same over here, and he gets deflected. But when you make the slit smaller, right? What happens? You get more. You're going to hit the sides more, right? Here you barely hit it. Now you made it so that now you're encompassing. Oh, you're going to hit the sides big time on there, right? And you're going to start hitting it more and more on the, you know, this side of the slit than the other side of the slit, like over here, right? You will get more deflection. This will go off. Look at how these are going off like that, right? But look at this one. This one's going off. This one's going to these two things. This one probably goes to these if I would have lined it up. And then if you make it even smaller, look at deflection now. You got even more deflection. If I put this slit over here, the deflections would be going off past here. So you can see I drew it up here too. How, you know, you start out where they just barely touch the sides, and so that you barely have any deflection, right? Then it's make it smaller. Now you have bigger deflection. Make it smaller even more. You make even more deflection. And the whole thing is, the more interference you get, the more you can see, the more you're pushing it out to the outsides. The smaller it is, you can see, you know, more of the light from these fringes go in. Now, so what happens? You make a hole that's too big that you can't hit the sides. You just get clumps like this. You get a circle. make it smaller, right? And look, he's still